Have you ever wondered what actually happens to a massive, multi-million-dollar AI training run when just one single microchip fails? I mean, when you're dealing with computing clusters literally the size of football fields, hardware failure, whether it's just from component degradation or hitting thermal limits, it isn't just a possibility, it is an absolute mathematical certainty. So, does the system just shrug it off? Or does one broken chip bring the entire operation to a grinding, incredibly expensive halt?
Welcome to The Explainer. Today we are diving into a really fascinating new paper from Google DeepMind and Google Research that tackles this exact vulnerability head-on. They introduce a groundbreaking framework called Decoupled Diloco, and honestly, it is a complete reimagining of how we coordinate thousands of AI accelerators. It takes them from being this fragile, tightly coupled monolith and turns them into a resilient, decentralized network. It's a real game changer.
All right, let's jump in. Here's our roadmap for today. First, the billion-dollar bottleneck. Second, rethinking the CAP theorem. Third, enter decoupled Diloco. Fourth, asynchronous learners and syncers. Fifth, embracing chaos and scavenging. And finally, number 6, the future of pre-training.
Section 1, the billion-dollar bottleneck. To really appreciate this solution, we first need to understand the sheer scale of the problem. Modern pre-training relies incredibly heavily on something called the Single Program Multiple Data, or SPMD paradigm. Basically, every chip runs the exact same program on different chunks of data, but they are tightly coupled. They literally have to talk to each other and agree on the model's parameters at every single step. So if just one accelerator has a transient slowdown or a network hiccup or completely fails, the entire global computation just stalls. The blast radius of that one tiny failure is the whole multi-million-dollar system. It's kind of like a massive marching band, right? If one person trips, the entire band has to freeze in place until that one person stands back up.
In a standard data parallel system, a localized failure hits, and boom, you get massive global downtime. Everything stops while the system figures out the error, reconfigures, and restarts. It's a nightmare. But with a decoupled system, it's a totally different story. A failure might hit one local group, sure, but the rest of the entire system, it just keeps on stepping. It doesn't even blink.
Section 2, rethinking the CAP theorem. So to fix this glaring vulnerability, the researchers borrowed an idea from distributed systems engineering. They framed the problem using an analog of the famous CAP theorem. Now, in the context of pre-training, consistency means every single chip has the exact same synchronized view of the model weights. Availability means the training keeps running even if hardware fails, and partition tolerance means the system can survive unstable network connections. The problem is, prior systems foolishly prioritized perfect consistency to ensure the parameters didn't diverge. But man, that comes at the massive expense of everything else. When you contrast these two paradigms, the necessary shift becomes pretty obvious. That old SPMD paradigm rigidly sticks to perfect parameter consistency, which leaves it completely vulnerable to those catastrophic global stalls. So the researchers decided, okay, let's build a system that prioritizes availability and partition tolerance instead. By relaxing those incredibly strict synchronization rules, they ensure the system maximizes its goodput. And goodput just means the hardware as a whole never stops doing useful learning, even if chunks of it are temporarily completely broken.
Section 3, enter decoupled Diloco.
And that brings us to the hero of our story, Google's Decoupled Diloco framework. The core idea here revolves around independent learners. These are groups of chips doing the heavy lifting of the actual training. Instead of waiting around for some monolithic global update, they process sharded fragments of the model entirely at their own pace. Imagine one learner unit completely stalls out for a few steps. Instead of taking the whole system down with it, a central syncer and the other healthy learners just keep seamlessly exchanging data and updating the model. The blast radius of the failure is strictly contained to that one single stalled learner. No global downtime.
Section 4, asynchronous learners and syncers.
Okay, so how do they pull off this asynchronous magic without totally ruining the AI's learning process? It boils down to 4 clever steps. First, the independent learners crunch through their own data shards locally. Second, they chop the model up into fragments and asynchronously fire their updates off to a central syncer. Third, and this is key, the syncer doesn't wait around for everyone. It just waits for a minimum quorum of learners to check in before it applies a larger optimization step.
And fourth, because these learners are inevitably running at different speeds, the syncer uses dynamic token-weighted merging. Basically, if a super-fast learner processes 1,000,000 tokens and a slower one processes 500,000, the fast learner's updates are given exactly twice the weight. It is brilliantly robust. And the physical layout of this architecture is really smart. The heavy lifting is done by those learners, which are clusters of specialized TPU chips. But the central synchronizer state, that lives entirely on standard, highly stable CPU-only hosts. This isolation is absolutely crucial. If a whole group of TPUs literally catches on fire, the central CPU synchronizer just calmly marks that learner as absent and continues coordinating the rest of the healthy cluster over the network.
Section 5. Embracing chaos and scavenging.
So to test this in real-world disaster scenarios, the researchers unleashed some chaos engineering. They simulated heavy hardware failures, think random node preemptions and massive network drops, across millions of chips. And the results? Honestly, they are stunning. Under heavy failure rates, your standard data parallel training crashes to a miserable 27% goodput. Even elastic methods that try to dynamically resize the cluster, they only hit 58%. But Decoupled Diloco achieves a massive 88% goodput, with strictly zero global downtime. It just keeps churning out useful work.
This leads to a massive scaling advantage, perfectly summarized by this rule of thumb from the paper. Because Decoupled Diloco isolates the blast radius of failures, a system with many independent learners mathematically matches the efficiency of a tiny, totally failure-free system. Let's put that into perspective. If you have 100 learners and one fails, it barely makes a dent in the other 99. But in a monolithic system, that one single failure brings all 100 to a dead stop. Basically, you are no longer penalized for scaling up.
And because the framework completely drops the need for strict synchronization, it unlocks a concept that is incredibly cool, called scavenging. Think about it. There are chunks of unused compute power scattered in data centers all across the globe. Decoupled Diloco can seamlessly scoop up those spare resources on the fly, adding temporary learners to the training run without ever pausing the main system. You can even mix older, slower chip generations with brand new ones. Because of that token-weighted merging we talked about earlier, the system naturally accepts the slower updates whenever they finally arrive without ever forcing the ultra-fast chips to wait around.
Section 6. The future of pre-training. Okay, so we've seen that this architecture is virtually indestructible and highly efficient. But I know what you might be wondering. Does this chaotic, asynchronous mess actually produce a smart AI? Well, when they compared standard, tightly coupled models against the decoupled Diloco models across really tough benchmarks for text and vision, the performance was practically identical. Let that sink in. Despite the asynchronous updates, the totally varying learner speeds, and the heavy simulated hardware failures, the final machine learning capability is completely uncompromised. The model is just as capable as one trained under perfect laboratory ideal conditions. This paper fundamentally upends how we think about building AI supercomputers. By moving away from that rigid, lockstep synchronization and instead prioritizing availability, we can extract massive amounts of useful computation from unpredictable, unreliable hardware. And honestly, it leaves us with a truly mind-bending thought. If we no longer need all our chips perfectly in sync, sitting in the exact same building, what kind of massive, decentralized AI could we build if we just started scavenging every single spare microchip on Earth?